Chapter 16, Part 2 of Volume 3, Airplane Flying Handbook, FAA-H-8083-3A. This LibriVox recording is in the public domain. Engine failure after takeoff. Single engine. The altitude available is, in many ways, the controlling factor in the successful accomplishment of an emergency landing. If an actual engine failure should occur immediately after takeoff and before a safe maneuvering altitude is attained, it is usually inadvisable to attempt to turn back to the field from where the takeoff was made. Instead, it is safer to immediately establish proper glide attitude and select a field directly ahead or slightly to either side of the takeoff path. The decision to continue straight ahead is often difficult to make unless the problems involved in attempting to turn back are seriously considered. In the first place, the takeoff was in all probability made into the wind. To get back to the takeoff field, a downwind turn must be made. This increases the ground speed and rushes the pilot even more in the performance of procedures and in planning the landing approach. Secondly, the airplane will be losing considerable altitude during the turn and might still be in a bank when the ground is contacted, resulting in the airplane cartwheeling, which would be a catastrophe for the occupants as well as the airplane. After turning downwind, the apparent increase in ground speed could mislead the pilot into attempting to prematurely slow down the airplane and cause it to stall. On the other hand, continuing straight ahead or making a slight turn allows the pilot more time to establish a safe landing attitude, and the landing can be made as slowly as possible. But, more importantly, the airplane can be landed while under control. Concerning the subject of turning back to the runway following an engine failure on takeoff, the pilot should determine the minimum altitude an attempt of such a maneuver should be made in a particular airplane. Experimentation at a safe altitude should give the pilot an approximation of height lost in a descending 180-degree turn at idle power. By adding a safety factor of about 25%, the pilot should arrive at a practical decision height. The ability to make a 180-degree turn does not necessarily mean the departure runway can be reached in a power-off glide. This depends on the wind, the distance traveled during the climb, the height reached, and the glide distance of the airplane without power. The pilot should also remember that a turn back to the departure runway may in fact require more than a 180-degree change in direction. Consider the following example of an airplane which has taken off and climbed to an altitude of 300 feet AGL when the engine fails. Figure 16-5. After a typical 4-second reaction time, the pilot elects to turn back to the runway. Using a standard rate 3-degree change in direction per second turn, it will take 1 minute to turn 180 degrees. At a glide speed of 65 knots, the radius of the turn is 2,100 feet. So at the completion of the turn, the airplane will be 4,200 feet to one side of the runway. The pilot must turn another 45 degrees to head the airplane toward the runway. By this time, the total change in direction is 225 degrees, equating to 75 seconds plus the 4-second reaction time. If the airplane, in a power-off glide, descends at approximately 1,000 feet per minute, it will have descended 1,316 feet, placing it 1,016 feet below the runway. Emergency descents. An emergency descent is a maneuver for descending as rapidly as possible to a lower altitude or to the ground for an emergency landing. Figure 16-6. The need for this maneuver may result from an uncontrollable fire, a sudden loss of cabin pressurization, or any other situation demanding an immediate and rapid descent. The objective is to descend the airplane as soon and as rapidly as possible, within the structural limitations of the airplane. Simulated emergency descents should be made in a turn to check for other air traffic below and to look around for a possible emergency landing area. A radio call announcing descent intentions may be appropriate to alert other aircraft in the area. When initiating the descent, A bank of approximately 30 to 45 degrees should be established to maintain positive load factors, G-forces, on the airplane. Emergency descent training should be performed as recommended by the manufacturer, including the configuration and airspeeds. Except when prohibited by the manufacturer, the power should be reduced to idle, and the propeller control, if equipped, should be placed in the low pitch or high revolutions per minute (RPM) position. This will allow the propeller to act as an aerodynamic brake to help prevent an excessive airspeed buildup during the descent. The landing gear and flaps should be extended as recommended by the manufacturer. This will provide maximum drag so that the descent can be made as rapidly as possible without excessive airspeed. The pilot should not allow the airplane's airspeed to pass the never exceed speed, VNE, the maximum landing gear extended speed, VLE, or the maximum flap extended speed, VFE, as applicable. In the case of an engine fire, a high airspeed descent could blow out the fire. However, the weakening of the airplane structure is a major concern, and descent at low airspeed would place less stress on the airplane. If the descent is conducted in turbulent conditions, the pilot must also comply with the design maneuvering speed, VA, limitations. The descent should be made at the maximum allowable airspeed consistent with the procedure used. This will provide increased drag and, therefore, the loss of altitude as quickly as possible. The recovery from an emergency descent should be initiated at a high enough altitude to ensure a safe recovery back to level flight or a precautionary landing. When the descent is established and stabilized during training and practice, the descent should be terminated. In airplanes with piston engines, prolonged practice of emergency descents should be avoided to prevent excessive cooling of the engine cylinders. In-flight fire. A fire in flight demands immediate and decisive action. The pilot, therefore, must be familiar with the procedures outlined to meet this emergency, contained in the AFM/POH for the particular airplane. For the purposes of this handbook, in-flight fires are classified as in-flight engine fires, electrical fires, and cabin fires. Engine fire. An in-flight engine compartment fire is usually caused by a failure that allows a flammable substance, such as fuel, oil, or hydraulic fluid, to come in contact with a hot surface. This may be caused by a mechanical failure of the engine itself, an engine-driven accessory, a defective induction or exhaust system, or a broken line. Engine compartment fires may also result from maintenance errors, such as improperly installed/fastened lines and/or fittings resulting in leaks. Engine compartment fires can be indicated by smoke and/or flames coming from the engine cowling area. They can also be indicated by discoloration, bubbling, and/or melting of the engine cowling skin in cases where flames and/or smoke is not visible to the pilot. By the time a pilot becomes aware of an in-flight engine compartment fire, it usually is well developed, unless the airplane manufacturer directs otherwise in the AFM/POH. The first step on discovering a fire should be to shut off the fuel supply to the engine by placing the mixture control in the idle cutoff position and the fuel selector shutoff valve to the off position. The ignition switch should be left on in order to use up the fuel that remains in the fuel lines and components between the fuel selector/shutoff valve and the engine. This procedure may starve the engine compartment of fuel and cause the fire to die naturally. If the flames are snuffed out, no attempt should be made to restart the engine. If the engine compartment fire is oil-fed, as evidenced by thick black smoke, as opposed to a fuel-fed fire, which produces bright orange flames, the pilot should consider stopping the propeller rotation by feathering or other means, such as with constant speed propellers, placing the pitch control lever to the minimum RPM position, and raising the nose to reduce airspeed until the propeller stops rotating. This procedure will stop an engine-driven oil or hydraulic pump from continuing to pump the flammable fluid which is feeding the fire. Some light airplane emergency checklists direct the pilot to shut off the electrical master switch. However, the pilot should consider that unless the fire is electrical in nature or a crash landing is imminent, deactivating the electrical system prevents the use of panel radios for transmitting distress messages and will also cause air traffic control, ATC, to lose transponder returns. Pilots of powerless single-engined airplanes are left with no choice but to make a forced landing. Pilots of twin-engine airplanes may elect to continue the flight to the nearest airport. However, consideration must be given to the possibility that a wing could be seriously impaired and lead to structural failure. Even a brief but intense fire could cause dangerous structural damage. In some cases, the fire could continue to burn under the wing, or engine cowling in the case of a single-engine airplane, out of view of the pilot. Engine compartment fires, which appear to have been extinguished, have been known to rekindle with changes in airflow pattern and airspeed. The pilot must be familiar with the airplane's emergency descent procedures. The pilot must bear in mind that the airplane may be severely structurally damaged to the point that its ability to remain under control could be lost at any moment. The airplane may still be on fire and susceptible to explosion. The airplane is expendable, and the only thing that matters is the safety of those on board. Electrical fires. The initial indication of an electrical fire is usually the distinct odor of burning insulation. Once an electrical fire is detected, the pilot should attempt to identify the faulty circuit by checking circuit breakers, instruments, avionics, and lights. If the faulty circuit cannot be readily detected and isolated, and flight conditions permit, the battery master switch and alternator/generator switches should be turned off to remove the possible source of the fire. However, any materials that have been ignited may continue to burn. If electrical power is absolutely essential for the flight, an attempt may be made to identify and isolate the faulty circuit by 1. Turning the electrical master switch off, 2. Turning all individual electrical switches off, 3. Turning the master switch back on, 4. Selecting electrical switches that were on before the fire indication, one at a time, permitting a short time lapse after each switch is turned on to check for signs of odor, smoke, or sparks. This procedure, however, has the effect of recreating the original problem. The most prudent course of action is to land as soon as possible. Cabin fire. Cabin fires generally result from one of three sources. 1. Careless smoking on the part of the pilot and/or passengers. 2. Electrical system malfunctions. 3. Heating system malfunctions. A fire in the cabin presents the pilot with two immediate demands: attacking the fire and getting the airplane safely on the ground as quickly as possible. A fire or smoke in the cabin should be controlled by identifying and shutting down the faulty system. In many cases, smoke may be removed from the cabin by opening the cabin air vents. This should be done only after the fire extinguisher, if available, is used. Then the cabin air control can be opened to purge the cabin of both smoke and fumes. If smoke increases in intensity when the cabin air vents are opened, they should be immediately closed. This indicates a possible fire in the heating system, nose compartment baggage area, if so equipped, or that the increase in airflow is feeding the fire. On pressurized airplanes, the pressurization air system will remove smoke from the cabin. However, if the smoke is intense, it may be necessary to either depressurize at altitude if oxygen is available for all occupants, or execute an emergency descent. In unpressurized single-engine and light twin-engine airplanes, the pilot can attempt to expel the smoke from the cabin by opening the foul-weather windows. These windows should be closed immediately if the fire becomes more intense. If the smoke is severe, the passengers and crew should use oxygen masks if available, and the pilot should initiate an immediate descent. The pilot should also be aware that on some airplanes, lowering the landing gear and/or wing flaps can aggravate a cabin smoke problem. End of Part 2 of Chapter 16.